that case, hello all, I'm Susmit Sarkar, and I'll be speaking about work that I did with many fine people, in particular Andres Coens, who is currently at Amsterdam, and Soham Chakraborty, currently at TU Delft, and lots of their students and co-workers, and so on. So I'll take you through what we call compound memory models, and I'll try to explain what that means. So this is, in part, work that was described in a PLDI paper from last year. Many of you may have seen versions of the first part of my talk before. And then I'll talk a bit more about some things that we tried to fix in that paper, some things we didn't quite like and what we might do about them. And at the end, I'll end with incoherent philosophical mumblings if I get there. So what's compound memory models? Have a slide for what memory consistency models are for any who might not be very familiar or might have forgotten, just to remind you. So what memory consistency models are is we start with the observation that the standard interleaving model of concurrency, if we apply that to shared memory concurrency, that basically means that all threads have a consistent view of memory at all time. And this was formerly called sequential consistency a long time back by Lamport. It's kind of the orthodox classical model of concurrency. Yeah. It's a fact, fortunate or unfortunate, that no modern piece of hardware, multi-threaded hardware, actually does give you sequential consistency. Instead, you get various kinds of what's called weak memory models or relaxed consistency models. To show you an example, and to fix my notation, because everybody in weak memory has slightly different notation, here's a fairly simple test. It's called, for those in the know, MP or message passing. And what it is two threads, thread 0 and thread 1, running this program on two shared memory locations, x and y. So initially, x and y are both initialized to 0. And over here, thread 0, it writes 1 to x, and program order later writes 1 to y. Meanwhile, concurrently, thread 1, the reading thread, does two reads, and it reads those locations y and x in the opposite order. Okay? And what we want to see is, well, what values do we observe in these reads? And in particular, we ask the question, is it ever possible in the very same execution for the first read of y here to read 1, whereas the next read here from x to read 0? If that were to be the case, that would mean that because this is the only thread writing to y, it must have read this particular write here. Whereas if this read is reading 0 from x, that means it must not be observing that write of x. It must be observing the initial write. Okay? So in sequential consistency land, the classic interleaving model, any interleavings you do, because program order has to be respected, you'll get that in the very same execution, you can never see R1 equals 1 and R2 equals 0. And that's actually the case not just in sequential consistency, but in other memory consistency models as well. In particular, on the x86 TSO model, which is the memory model of Intel and AMD processors, you'll never see this result. It's forbidden architecturally. Whereas on some other architectures, in particular on ARM and Power, it is architecturally allowed. And in fact, you will see this kind of result if you run this test for real. So what that means is that we don't have a relaxed memory consistency model. We have models, many different ones, depending on which architecture you happen to run on. And these architectural models are usually speaking weaker than any particular implementation, in the sense that the architectural models allow sometimes behavior that you may not be able to observe on particular brands of hardware that you have sitting on your desk. Because these architectural models, they are trying to cover the range of possibilities that they might choose to implement. So anyway, this is a story that we have been telling for a few years. It used to be, in the olden days, I used to stand up and say, there's so many different models, the differences are subtle, nobody knows what they are, even the guys who make them don't know what they are. Life is tough. And in some ways, we have succeeded, right? Lots of people, some in this room, many outside, have worked on these models for a while, and we have a pretty good idea of what the memory consistency models are, at least. Sorry, Ben, if just for user space programs. For many different architectures, x86, Power, ARM, RISC-V, and so on. And this is, great news. It's big specification. Well, okay, maybe medium specifications, but pretty nailed down specifications. So that was all good. But then people started building other kinds of machines as well. So in particular, in the last decade or so, people have been wanting to program on GPUs, who knows why. And GPUs, they have memory consistency models if you do shared memory concurrency on them, just like on any other piece of hardware. And they have, depending on the architecture, several different memory consistency models. The one that's best defined is the PTX memory consistency model, so-called. It describes what the NVIDIA GPUs promise to give you. And lots of work has gone into this as well, mostly by Dan Lustig and his friends. So I don't know how many people program GPUs. I certainly don't very much. I have looked at a lot of GPU programs, but I don't much program them. But things you have to know about GPU programs from for the purposes of this talk is that you get lots of threads, really lots and lots of threads of the order of thousands. And to program these in any sensible fashion, what GPU programmers like to do is to program them in sort of blocks which are arranged hierarchically. Okay, so you run a bit of your program on a small block of 32 threads, and some other part of the program on some other 32 threads, and so on. And these are arranged in kind of a hierarchic fashion. So what that means for memory consistency world is that GPU memory models, PTX certainly, are what we call in the trade non-multi-copy atomic, which is just this idea that events are not necessarily propagated to all the threads at exactly the same time. And this the GPU programmers and GPU makers think is fairly important for them to be able to run these thousands of threads concurrently. There's also memory consistency models on GPUs have this notion of scopes to deal with this kind of hierarchical block nature of GPU programming. And what that means is you can say that using fences and barriers and things like this, that this barrier should take effect only within a particular small block or a slightly bigger scope consisting of 4 blocks, or a barrier that takes effect across the whole system, and so on. So you can sort of annotate your barriers and other synchronization mechanisms in this way. Okay. By the way, I should have said before, please ask questions at any point, because much as I love the sound of my own voice, it's probably not ideal. Yes, sir.
Do these scopes, maybe I missed it, do these scopes are they hierarchical?
They are hierarchical, yes. So there's tree kind of topology on these blocks, yes.
Fixed by a particular hardware or by?
Fixed by the hardware you're running on, yes.
Different from one NVIDIA thing to another?
So they are all tree structured. That's, I think, the thing to say first. And it does depend sort of how many threads you have in a block and how many blocks you have in a super block and that kind of thing on different hardware. But you typically do have 3 levels of hierarchy.
So the scopes are fixed in the hardware?
Yes. Absolutely. Okay. So all of this was incorporated in the PTX memory model I just spoke of from NVIDIA. So this is kind of old work, although it's still kind of interesting to look at and ponder the differences between other memory models we might be used to. But anyway, the world moves on, and many hardware manufacturers want to put CPU and GPUs on the same chip, or really same system, SoCs really. The big example is NVIDIA's Grace Hopper chip, very well named, putting together what they call a Grace class CPU together with a Hopper class GPU on the same board that you can get, with various kinds of very fast interconnects between them on chip to make them operate on the same piece of memory. And this is already announced. I don't believe you can physically get your hands on one yet, but very soon now. And NVIDIA is not the only example of this. AMD and Intel are exploring things like this as well. So, as a memory model person, I ask, what should the memory model of those systems be? And that question can be from many different angles. What should it be for programming on these darn things? Or maybe you want to reason about these programs like some of us want to do. And it's also an interesting question to ponder from the view of implementations. And here I speak of implementations both from the hardware side. What should the hardware people try to implement so as to make everybody else's lives a bit easier? Not that that has stopped before, but also implementations from compiler writer's side. Given that the hardware is going to do something, hopefully sane, what should the compiler writers be doing? So, to be concrete, let me take the example of not CPU, GPUs, but perhaps CPU models, which is perhaps a bit more familiar. So let's say we have a system in which some of our threads are put on x86 kind of cores, and some of our threads are put on ARM kind of cores, while still sharing the same memory. And this is not quite as outlandish as it sounds. You could have systems like this in sort of cloudy kind of devices. So what should the memory consistency model be? So one proposal might be, let's take the consistency of the model, the combined model of this x86 and ARM, to be the stronger of the two. Stronger meaning achieving the meat of the behaviors possible. And that's not quite a good model for these, because imagine if we posited such a model and we happen to run our program all on the ARM cores. Then that would mean that the program I showed you before, which recall is is forbidden on x86 but allowed on ARM, to be in the model forbidden, and therefore that would not be good if all the threads were running on ARM kind of cores. So the model would be stronger than reality, and that's no good. So different proposal might be, let's consider the consistency model to be the weaker of the two. And in this case, because ARM has a weaker model, we would say that everything must behave like an ARM. And here we have kind of the dual problem, right? If we happen to run our programs all on x86 kind of cores, then, like I said before, x86 will never show the weak behavior on that particular test. But our model will say, oh, it might happen, and therefore you might be forced to put in additional barriers unnecessarily, and that will slow down programmers. So that's not quite good either. So let's look at the problem from maybe a more programmer-centric way, which might help. By recalling to ourselves that, for example, the C and C++ memory model, C11, it's supposed to have a model that can be implemented on all hardware, right? With various kinds of mappings and compiler tricks to make sure that you are doing the right thing on the different implementations. And this was obviously a design criteria, and it has to a large measure been fulfilled. On all the major architectures, we have known mapping schemes for compilers to follow so that, in fact, the compiled programs have the same or stronger semantics than the source program in the C11 memory model. And this has also been extended, again, for PTX by what they call scoped RC11 model, which is a version of the C11 model which introduces to C a notion of scoped release acquire and scoped fences. And then again, there's mapping schemes down to PTX that do the right thing for those programs. So our proposal is that in a compound memory model where parts of your program are running on different architectures, it should be possible to reuse the architecture-specific compiler tricks, the compiler mappings, depending, of course, on the architecture the thread is running on. And the principle we are going for is that compilers for x86 should not have to change just because part of the program is running on some other kind of architecture. And similarly for every other kind of major architecture. Yes, question? Sorry.
We also see this sort of behavior when we're talking to devices that are doing DNA and stuff.
Oh, absolutely, yes. So, and I think similar kinds of problems would happen there. We haven't, in this work, looked very much in that, but I know Brijesh has been working quite a lot on, for example, RDMA and things like this. And absolutely, the same kinds of issues, and I think, hopefully, similar principles of solutions should transfer.
There you have different points of coherence, right? Here and outer.
Yes. Yeah. Right. Where was I? Yeah. So that's our kind of proposal. So how does that proposal work? So for example, let's take that message passing test and say that the writer thread is up here on x86, and the reader thread we have put on a ARM kind of core. In this case, x86 would say those two stores would go in order, but ARM would say those two loads, they can go out of order. And even if the stores were in order, kept in order, in program order that is, if you are allowed to reorder the loads as ARM would do, then you would observe the non-sequentially consistent behavior of R1 equals 1 and R2 equals 0. So that program should allow this kind of behavior if we schedule it in this way. If we did want to forbid it, we would have to stop that kind of reordering on ARM. And there's many different ways of doing it. One of the ways in doing it is to upgrade the load here of y to what ARM would call a load acquire. And that would mean that these two loads will not be reordered. And in this case, our proposed model would be that the non-sequentially consistent execution would be forbidden, even though on x86 we didn't put in any barriers, because x86 they just keep those two stores in order naturally, as it were, in a x86 core. Okay. Right. So that's our proposal. Can we get there? So to answer the question of can we get there, we'll have to think a bit about how memory consistency models do come about in hardware. And from the study of memory consistency, we know that the kinds of non-sequential consistent behavior we see, it comes from all kinds of thread local reorderings that all architectures allow, as well as properties of the interconnect that several architecture models try to model. Yeah. So the thread local part, even in a heterogeneous or compound setting, works just the same as they do in the individual architectures. So x86 reorderings, thread local reorderings are just the same as your standard x86 cores would do. Similarly for ARM and similarly for RISC-V, and actually similarly for GPUs such as PTX. Yes, question?
Is the claim that all of the weak memory models can be characterized by reorderings? Because I thought that there was a characterization like that for TSL x86, but not for any other weak memory.
For reorderings plus reorderings done by the interconnect, which is not thread local reorderings, if that makes sense.
Still
I
seems
think it's nice, more instructive to just not use the word reordering, but talk about out of order instead, or even out of order and speculative.
So you're proposing replacing reorderings by out of orderings.
Yeah, because reorderings does.
Okay, yeah.
People aren't familiar with the hardware, which most people, it does suggest that they are reordering things, which they're not really.
so you only consider permutations as the sequential.
Okay, yes.
approach. That sounds like very strong.
Right, so that's not what I was getting at, and yeah, fair enough. Maybe, what should I say, it comes from thread doing stuff and interconnect doing stuff. How about that? The stuff being, as Peter was mentioning, out of ordered accesses, speculations, and all these kind of things.
So it might be that there's some interesting behaviors between the interconnect and the point of coherency for the CPU, where there might be buffers and caches in between those things.
Yeah, so the interconnect is
So
all of the interconnect, all of the gadgetry that's interconnecting the different threads.
right, including the bits that might be in the CPU, but between the outermost caches and.
Yeah, absolutely.
I didn't really think about that.
David. Is he not? Well. Right. Where was I? Yeah, I was talking about the thread local stuff being just the same as before. Yes.
Maybe one other question is that sometimes if you have a given weak memory model, it's not obvious or easy to decide whether such and such behavior
Oh,
comes
absolutely,
from
absolutely.
which sides, or it could come from both sides.
It could come from both, indeed. Yes.
Like, yeah, is there a way to determine which side, or do you just take the weakest approach of if it could be explained by both sides, you do it on both sides?
soldering iron in a very steady
I
hand.
I
Try
haven't-
to cut out the.
I haven't considered the problem in exactly
the
that
3 nanometer
scenario. And in many cases, it's easier to see it's on one side of the boundary.
Yeah.
But of course, there is.
Yeah, but the thing is
Sort of
that what
gray
I'm saying is that
area.
if you consider that, for example, a read reordering out of order comes from a thread local, or it comes from being made out of order lower down the stack. The
Oh yes, it could
the
come from
compound
both.
model that you
Yeah.
will get from those two interpretations might be different.
And indeed, you could do both. Yeah.
Okay.
I lost my thread, as it were. Yes. So I was saying that perhaps the thread doing its stuff remains the same, but the interconnect certainly could be doing more stuff, and indeed might be doing more stuff. In particular, because it's fusing together, different architectures which have, different characteristics. So in principle, one might think the interconnect could be doing an arbitrary thing of stitching together these models. And one of my messages of this talk is that actually designers are not quite that arbitrary. So, of course, CPUs and GPUs and all these heterogeneous systems, they are stitched together using very clever stuff in the interconnect. So there's things like inter-device coherence protocols. There are many examples, well, not many, a relatively bounded number of examples of same, like CHI, CXL, and so on. And the point of these is that the hardware designers, they do relatively simple stuff when they are trying to put together heterogeneous systems, because this is for various hardware reasons at the last level of the cache are speaking to each other. And at that point, what hardware folk prefer to do is reasonable for them to do for basically a combination of performance and correctness, and the trade-off between them is to do basically a simple invalidation kind of protocol. And there's various implications of that. For example, they follow this kind of protocol of having a single writer, but possibly multiple shared readers of every location at every point. That's kind of the invariant they have in their heads. And these are, not the full spectrum of complex cache protocols that you might expect. But for, yes.
It seems very un-hardware architect-like to not be insanely complicated. Surely, even if it isn't today, it will be tomorrow.
Who can speak for what might happen tomorrow? But, there are good hardware reasons, which I don't know that I'm competent to explain. If you are putting together cache protocols on the same physical board, connecting just the last layer of caches together, and not reaching deeper into the cache hierarchy on either side, because that's not something they want to spend their efforts on, then you only get a relatively simple class of cache protocols. And we test this on everything we can test and find that they do indeed do the simple stuff. But as you say, what might happen tomorrow is unknown. But if we do have that world in which that protocol is, well, not simple exactly, it's still fairly complex, and there's all kinds of clever tricks that they play. But the semantic results of that, of those kinds of cache protocols, summarized usually by this kind of single writer, multiple reader invariant, is semantically speaking simpler. And what we did was we tried to model that kind of world operationally using an adaptation of one of our old models, a partial order propagation model. The idea there is that you propagate along, when you are propagating events from thread to thread, you propagate certain order constraints to go with those events, observable events. And this is kind of an acronymization. Local orderings by stalling on threads principle, or LOST, because we wanted to call it lost pop. Essentially, really, the principle says that the propagations of writes, the orders that we are propagating on in this partial order, are only the locally defined order before relations. And what that means is the locally defined could be particular to the architecture of the thread, and in particular could differ from thread to thread depending on which architecture they are evoked.
Why did you need to remember that order? I mean, unless I'm misunderstanding, it feels like you're saying that you need to remember the locally ordered before order between writes in the cache hierarchy or in your interconnect.
So here I have sort of shifted slightly to like our model,
Okay.
the operational model that we sort of abstract away from the interconnect world I was explaining to you before.
Okay.
And
So
in
it's
this,
just, it's just the default. I wait until everything I need to wait for before happens.
it's, yeah,
before
exactly
something
so.
Yeah. Okay.
Everything that I need to wait for, where the decision you make about what do I need to wait for is made sort of thread locally. That's kind of the point I'm getting at. Yeah.
I think I already asked a question when Andreas gave the talk at PLDI, but there's a sort of weird thing that you've done, which is you've given this characterization that was sort of very high level and very axiomatic, like, there's like the thread local ordering, and then there's the propagation between threads. And then suddenly you jump on an operational model that is kind of, they're very intentional, right? And it's
That's I think a fair thing to say. So the thing I would say is it's kind of a abstraction, right? It's a model. And what my previous words map on to this model is there is all kinds of thread speculation and thread reorderings out of orderings, that you are used to in a thread local context. And when it comes time to propagate information from thread to thread, then we follow this kind of locally defined before kind of thing. So that's where the interconnect bit comes in, if that helps.
Have you thought about making an axiomatic version of this?
Yes, we have, and we did.
Oh, okay. Excellent. Then I'll just wait.
Well, I don't think I have very many slides on that, but I'll be happy to talk to you about it after. Right, I think mostly I've said all of this already. Is this kind of gets this kind of operational model that gives us the kind of properties we need. In particular, that the orderings you need to wait for, as I was just mentioning, is very much thread local, and it doesn't matter if the thread local bit is different for different threads depending on which architecture they're running on. And that gives us probably the mapping we want, with an asterisk that I'll come to. But what we get is this kind of compositionality property, sort of, that if each thread is compiled with a mapping scheme which is correct for the architecture running that thread, then the composed program has the same semantics, stronger semantics than it's a correct compilation of the source RC11, possibly with scopes if you're on GPUs semantic. And to do this proof, we derived an axiomatic model, which is sound with respect to this operational model I just sketched out. It's weaker in some known ways because, well, that's how axiomatic models work, but still strong enough to prove the kind of C11 correct compiling property that we were looking for. Sorry. Yes.
So was that C11 or RC11?
It's RC11, but with scopes. So imagine all of RC11, and then you have additionally each of your acquires, releases, and sequentially consistent accesses and barriers can further have a scope annotation. Okay. Right, so that's kind of the story we told in our PLDI paper. That's a good story, except that's not exactly what we did. And there's that asterisk there. So we didn't quite get there. What we got was that if each thread was compiled with compatible mappings, then the property I just mentioned on the previous slide would work. And what's compatible? You have to ask. Well, it means that the compilers on the different architectures are doing, well, compatible things. In particular, if you are familiar with the mapping schemes, then for many architectures, for example, for Power and ARM and RISC-V, I believe, there's at least two versions of the mapping scheme, one which works in a trailing fence kind of manner, put the fences after the respective axes as much as is possible, and one which is called the leading fence mapping, which puts the fence, the other direction. And if you compile the wrong architectures together with the wrong kinds of mapping schemes, then you won't get the compositionality property we were hoping for. So for example, what's an example? An example would be having two power clusters, some threads running on one cluster A and one on cluster B, where one is following the leading fence mapping and one is following the trailing fence mapping. And that we know definitely will not work. It would make not just our proofs break, but also probably miscompile RC11 programs. And I mean, that's just an example. There's many other architectures because, like I said, many architectures have this leading, trailing kind of fix. For example, PTX does as well, which means PTX plus ARM. Again, there's a question. That's actually an important one because PTX plus ARM is probably going to be one of the key architectures of these kind of heterogeneous systems. Okay. So what we actually did in our PLDI paper was that we proved that for many particular combinations, all of the ones on the slide, if we followed particular sets of different mappings on those architectures, then we would get the compositionality property. And we also showed, we knew that there were counterexamples if we had bad or incompatible combinations, for example, on Power and Power, or PTX and PTX, or ARM and PTX, and so on. Okay, so here's one of the ways in which it breaks. Many of you might have been able to imagine this just from my words on trailing and leading, but just in case that wasn't sufficient, here's a test that would show it would break. So here's a program, and first let's imagine we are in RC11 land. So this is a C program. So every time I say SC and release, they are kind of C style, sequentially consistent or release or acquire as the case may be. So it's a bit more complicated, but hopefully not too complicated. 4 threads this time. So thread 0, it's writing 1 to X using a sequentially consistent axis, and then writing 1 to Z using a release kind of axis. Everything is initialized to 0, by the way, just to make things clear. And then thread 1 is acquire reading from Z. And we are asking for the case in which that read reads 1, which means it reads from that release, and therefore there's a release acquire in the C sense, synchronization between those two. Okay. Next, thread 1 writes 1 in an SC kind of write to Y. And because RC11 has this property that sequential, the sequential consistency order, SC order, not sequential consistency order, SC order, incorporates, happens before intermediate edges. That means in particular that write of Y of 1 is in SC order after that write of X. Okay. And then there's some more stuff. Some more stuff is thread 2 writes 2 to Y. Because we are making a final observation at the end of time that Y is 2, that means that in SC order and in coherence actually, that write to Y comes before that. And then there's another kind of release acquire synchronization on A this time, or different location between threads 2 and 3. And then there's a SC read on thread 3. And question, can this SC read 0? Because the way RC11 works, in particular because, like I said, the SC order in RC11 incorporates happens before or release acquire synchronization in particular. Following this kind of chain, this is in SC order after that, and therefore cannot read from before it. So that's in RC11 land. If you happen to, if you compile it correctly with all leading or all trailing fence, then that would work because of the correctness properties of the compiler mappings. But if you miscompiled it so that the fences came on the wrong side, sorry, like here the fence corresponding to that SC was compiled before and there it was after, and so on, then the fences won't do you any good, basically. Right. So an observation, the counterexample depended on the writes propagating to different threads at different times. Or in other words, on the architecture being non-multi-copy atomic. So in fact, on multi-copy atomic hardware, and we can prove this, any arbitrary combination would work. Yes?
Just using on the previous thing, so people knew long ago that coherence of the mapping was essential.
Yes.
And morally that should be part of the ABRs. Has there been any movement towards making it be part of the ABRs? I wonder very optimistically.
It would be nice, but no is kind of the answer, because it turns out on different kinds of hardware doing one or the other is the better thing for just that hardware. And cross hardware compilation is not quite a thing yet. So there's not yet as much pressure for them to unify that ABI in the way you're looking for. I just looked at the clock and realized I have gone over time. So unless, I don't know if people want to escape for coffee, please feel free to walk in and out.
So the normal scheme is now we have 3 minutes and 38 seconds ago. Sorry, and then resume at 12:30.
Right.
So you can eat as much of the break as you think that they might reasonably stand for, but maybe not too much.
Okay, I'll carry on, and when I get the barrage of stones thrown, I'll stop. Yes. So, like I said, we can prove if every architecture in the world was multi-copy atomic, then the previous problem just wouldn't apply. So wouldn't it be nice if every architecture was in fact multi-copy atomic? x86 is, and both ARM and RISC-V are. One of the ones we care about though, PTX, it very definitely is not. Because like I said, GPUs have many different threads arranged in this kind of hierarchical block nature. And they really don't want it to be multi-copy atomic because that would be a bit aggressive to have thousands of threads having the writes propagated to and barriers if they were propagating at the same time. But also, these GPUs are structured quite hierarchically in the way I was describing before. So it seems like, and here I'm skating on even thinner ice, is GPUs are multi-copy atomic seemingly within the same block. As long as threads are in the same block, they get to hear of this events, write events in particular, at the same time. They most definitely don't see it at the same time when they're different threads don't see the same event at the same time if they're in different blocks. But in the same block, as far as we can test, they seem to be multi-copy atomic. So this is, just random tests we have run, right? The architecture is fairly clear, or at least the PTX formal model, as formalized, is fairly clear that you shouldn't be expecting any such property. But it is, yes.
Suppose, okay, this property actually holds
Yes.
limitations, which I can imagine. But is it some property that you can even think of exploiting from the software side? Because you do not know the size of the block, you might not even have much way to ensure that your threads are all scheduled on the same block. So why, in a sense, why does this property even matter?
Well,
You can control quite well on
you can, so
you can, yeah, I mean, it's
So one
you can
answer-
control on which precise block, but you can tell this
one,
32
one answer is that you can, in fact, fairly well control which threads are close together.
Oh, but close would mean
On the same block.
On the same block.
Yes.
Yeah.
Okay. Understood.
I mean, this is because you want to exploit locality, so you kind of need to be able to tell whether they're. So I think it's quite important to GPU programming that you can know where you are. I mean, where you are.
With respect to other threads.
Relatively.
Yeah,
not absolutely.
relatively
Yes,
speaking to other
you
threads.
don't know on which block of 32 thread you will run, but you know that all your 32 thread will run on the same one.
And that is kind of important for GPU programs.
And not just like a best effort version.
No, it will.
No,
run.
that's,
And actually, I mean, it's really something you have to take into account because sometimes there are constraints about shared execution because between the threads and whatever.
right. And one of the things we have been working on is to prove that, the property we want, the stronger property we want, rather, would work if we had a scoped MCA world. By which I mean, within a block, you're multi-copy atomic, and that property carries down hierarchically down the scopes. That makes sense. Thibaut.
But yeah, about this scope thing, I think that even on CPU hardware, like if you, for example, had an x86 plus ARM core, I would expect to have something where the ARM inside itself is multi-atomic and the x86 too has thread groups, but then the interconnect is later, and they are not really completely multi-copy atomic between the two. Or do they manage to have a cache coherence protocol that actually
So
provides
as-
instruction?
So all we need is that they are multi-copy atomic with their
Yeah, so
in their own cluster.
yeah.
We are not asking for multi-copy atomic all the way down to the entire
Yeah,
system.
but what I'm saying is that with that it would also work if you have just two different CPUs
Yeah,
on the
yeah.
same board or
Yes,
something like
yes, absolutely.
Yeah.
That's kind of the point. And like I said, all the ones we have managed to get our hands on do seem to follow this property of being scoped MCA. This is, by no means an exhaustive set of all GPUs that there are. It's just what we have been able to observe. Yes.
Is it sort of in terms of running tests and seeing what happens, or is it in sort of in terms of staring at the silicon and going, oh, it's doing something simple?
That's a good question. Mostly running tests, because we don't have our hands on silicon. On one of them, I forget which, I believe the AMD one, we have our hands not on silicon necessarily, but on a sort of Gem 5 version that they have also released. And again, yeah, staring at that. And in speaking with people who design cache protocols, this seems to be a reasonable model. Again, in the same kind of reasonable sense that we are wibbling about with Peter about this is what it is on today's hardware. But there seems to be good hardware reasons for these protocols to give us this kind of scoped MCA property. So that's me. Message is that GPU memory models are quite interesting, and putting them together with other kinds of models increases the interestingness factor. And as is typical, the architectural intent is not always easy to discern. But one of the things we found in doing this is that, in fact, the world is better than we imagined it is, because programmer requirements and properties of hardware do conspire sometimes to simplify the space of almost arbitrary models that you might have into something much more reasonable and something that we can prove some good properties about. So I had a separate slide on sort of vague wibblings, but I'll spare you that and maybe chat to you over coffee. What I had in mind was to sort of say that we have been working on memory models, but they're not very compositional, and they should be in many different kinds of ways. But that's a conversation to have for later. Thank you for your attention.